video 9. Planes may look incredibly heavy, but the reason they stay in the sky comes down to the fascinating science of aerodynamics. Aerodynamics explains how air moves around an aircraft and how four main forces, lift, drag, thrust, and weight, enact to create stable flight. Every part of an airplane is shaped and designed to control airflow, reduce resistance, and maximize efficiency. Even though a large aircraft like a Boeing 747 weighs over 400 tons when fully loaded, the forces of physics allow it to take off, cruise thousands of miles, and land smoothly. Lift is the primary force that keeps a plane in the air. It is generated by the wings, which are designed with a unique shape called an airfoil. An airfoil has a curved top and a flatter bottom, causing air to move faster over the top surface and slower underneath. According to Bernoulli's principle, faster moving air creates lower pressure, while slower moving air creates higher pressure. This pressure difference pushes the wing upward, creating lift. When a plane accelerates down the runway, enough air passes over the wings to generate sufficient lift to overcome its weight, allowing the aircraft to rise into the sky. Weight, on the other hand, is simply the force of gravity pulling the plane downward. The aircraft must generate enough lift to counteract its weight, or it cannot take off. This is why pilots carefully calculate weight limits before every flight, including fuel, passengers, cargo, and even weather conditions at the destination. Too much weight and the plane may require a longer runway, higher thrust, or might even be unable to take off safely. Thrust is the forward force produced by the aircraft's engines. For jet airliners, turbofan engines suck in massive amounts of air, compress it, mix it with fuel, ignite it, and blast hot gases out the back, pushing the plane forward. According to Newton's third law, every action has an equal and opposite reaction. So when the engine shoots air backward, the plane is pushed forward with equal force. Propeller-driven aircraft use spinning blades to create the same effect, pushing air backward to generate forward movement. Drag is the force that opposes thrust. It is essentially the air resistance created as the plane moves forward. The faster the plane flies, the stronger the drag becomes. That's why engineers focus heavily on making aircraft as streamlined as possible. Smooth curves, narrow shapes, and aerodynamic wings reduce drag dramatically, allowing planes to fly faster and more efficiently while consuming less fuel. Pilots control the balance between these four forces using control surfaces, ailerons located on the wings, control roll allowing the plane to tilt left or right, elevators found on the tail, control pitch raising or lowering the nose of the aircraft. The rudder, also on the tail, controls yaw, helping the aircraft turn left or right. By adjusting these surfaces, pilots maneuver the aircraft through climbs, descents, turns, and level flight. Even small adjustments can dramatically change how airflow interacts with the plane. One of the most interesting applications of aerodynamics is seen in high-speed aircraft. especially the supersonic Concorde. When flying at Mach 2, twice the speed of sound, the Concorde relied on extremely thin delta-shaped wings that produced lift efficiently at high speeds. At lower speeds, these wings generated vortex lift, where swirling air over the wings increased lift enough for takeoff and landing. Supersonic aircraft must deal with shock waves, rapid temperature changes, and intense drag, making their aerodynamic design far more advanced than traditional jets. Aerodynamics also plays a crucial role in preventing turbulence and maintaining passenger comfort. Pilots and aircraft systems work together to adjust wing positions, engine power, and altitude to find smoother air. Even though turbulence may feel dangerous, modern aircraft are designed to withstand far stronger forces than they ever encounter in real flights. The wing flexibility, strong materials, and continuous aerodynamic control allow the aircraft to handle rough air safely. Airflow around different parts of the aircraft is carefully managed to maintain efficiency. For example, winglets, the small upward tips at the end of wings, reduce vortex drag by preventing high-pressure air under the wing from spilling over the edges. This might seem like a small detail, but winglets can save airlines millions of dollars in fuel costs every year. Similarly, smooth fuselage surfaces, retractable landing gear, and optimized engine inlets all help reduce drag. Aerodynamics also affects landing and takeoff, two of the most critical phases of flight. During takeoff, pilots increase thrust to maximum power while adjusting flaps and slats on the wings to increase lift at lower speeds. These high-lift devices temporarily change the shape of the wing, allowing the aircraft to lift off the runway more easily. During landing, the opposite happens. Pilots use spoilers and flaps to reduce lift and increase drag, helping the plane slow down and descend smoothly toward the runway. Weather conditions like wind, temperature, and air density also impact aerodynamics. At high altitudes, the air is thinner, which reduces drag but also means less oxygen for the engines. Pilots and aircraft systems constantly adjust power settings and control surfaces to maintain efficient flight. Aerodynamics ensures stability even in strong winds, crosswinds, and varying temperatures, making air travel one of the safest modes of transportation in the world. Understanding aerodynamics helps us appreciate how airplanes achieve smooth, controlled, and safe flight. It's not just about engines or power, it's the careful balance of forces, airflow, and engineering precision. From small propeller planes to massive jets and even supersonic aircraft, aerodynamics makes flight possible and allows airplanes to cross oceans, climb above storms, and navigate the skies with remarkable reliability. Now that we've explored the science that keeps aircraft soaring through the air, next we will look at how landing gear supports airplanes during takeoff and landing, handling enormous forces with precision and strength.